Welcome back. So now we will start some of the advanced dynamic methods. So first we go through the stochastic dynamics. It says that the stochastic dynamics is the study of dynamical systems subject to the effect of noise or random fluctuation. It includes the implicit solvent effect. We'll see that what are the implicit solvent and explicit solvent methods. And it considers the impact of noise on the dynamical systems, which can significantly affect the behavior of systems, especially for the nonlinear systems, where the noise can act as the driving force leading to the modification of the deterministic dynamics. And it is important in the study of decision making. I mean, some of the examples are there. The fundamental concept in understanding the behavior of complex system under the influence of random fluctuations. Then example of the Brownian dynamics. So we all know what is the Brownian motion from our school level study. Okay, so that is a mathematical approach used to describe the dynamics of the molecular system in the diffusive regime. It is a simplified version of the Langevin dynamics, correspond to the limit where no average acceleration is present, making it particularly useful for the studying in dynamics in the molecular system in the diffusive regime. So understanding the behavior of the molecular system in the diffusive regime, it provides the framework of studying the dynamics in the complex systems for developing the new materials as well as the technologies. Then we move to the Langevin dynamics. So Langevin dynamics is a mathematical framework used to describe the motion of the particles in presence of friction as well as in noise. It is described by a stochastic differential equation that models the motion of particles under influence of friction and noise. And it has been applied to the field of diffusion. Okay, diffusion model, which provide the mathematical framework, understanding the diffusion process, etc. And it has been used to simulate the motion of particles in various complex systems such as polymer coils and in the diode solution. So now, when we do the energy minimization, that basically is the essentially comes under the optimization problem. So in that optimization problem, various computing algorithms are used. And first one is the steepest descent algorithm. So that this method is a first order iterative method. It utilizes the gradient based approach for the potential surface energy to minimize the energy of the system. Remember, in the first stage of the simulation, we do the energy minimization, which basically involves this kind of final application of this algorithms. It involves the moving in the direction opposite to the gradient to reach the local energy. It is commonly used in the energy minimization for any kind of MD simulation, allowing the system to relax and lower energy state by iteratively adjusting the atomic coordinates. Okay, further, this method guarantees the movement towards a minimum sum of squares without any divergence, provided that the value of certain parameters is approximately chosen, making it a reliable approach for energy minimization. This method is efficient per step and it may require more steps to find the minimum due to its approximation. Okay. Then there is another algorithm, that is the conjugate gradient algorithm. This conjugate gradient algorithm, this method is used to do the energy minimization and allowing the system to relax in a lower energy state iteratively, adjusting the atomic coordinates in a conjugate direction. It is more efficient than the steepest descent method as it minimizes the energy along with the conjugate direction, leading to faster convergence of minimum energy state. Then we use some of the constraint algorithm to fasten the simulation process, and these are these are collectively called as the constraint algorithm. So constraint algorithms are used to maintain the correct geometry of molecules during the molecular dynamics simulation, and so that the molecular dynamics simulation accurately represent the behavior of the system. So there are the implicit constraint forces such as atomic scale simulation, which reduces the computational cost associated with the explicit constraint forces, making them the preferred method and maintaining the correct geometry during MD simulation. It is applicable for the wide range of molecular systems. Again, uh, these algorithms are essential for the molecular modeling. Okay. So first one is the LINCS algorithm. That is the linear constraint solver algorithm. We will see that when we write the GROMACS script. That time we'll see that. So this LINCS algorithm is a non-iterative algorithm that always uses two steps, making it more stable and faster than some other algorithm. Okay, it can only be used with the bond constraint and isolated angle constraint, and is known for the stability and speed and making a valuable tool for efficiently maintaining the correct geometry of molecule during MD simulation. There is another thing that is called the shake algorithm. So it is used to maintain the bond constraint involving the hydrogen atom, like the CH bond in the MD simulation, and it takes. I mean, when the CH bonds are basically frozen, we can use the larger time step that will reduce the computational timing. So shake is stable algorithm that can be used to maintain the correct geometry of molecules. And its efficiency is maintaining the bond constraint and stability, making an essential tool for the study of molecular structure. There are some differences between applying the LINCS and the shake algorithm. So shake is an iterative algorithm, requires multiple iteration to converge, while LINC is a non-iterative algorithm that anyways converges within two steps. So basically LINC is a faster. So shake is used to maintain the bond constant involving the hydrogen atom, while LINC can be used for the bond constant for any type of atom. So shake is particularly with respect to the hydrogen. LINC is known for the stability and speed, making it a valuable tool for efficiently maintaining the correct geometry during MD simulation. But LINCS is reported to be 3 to 4 times faster than shake. Shake is widely used to maintain the bond constant in MD simulation, while LINCS are more general algorithm that can be used for any type of constraint. Now, so far, whatever we have discussed, this is mostly relying on the theory. But there are, I mean, reading the theory and subsequently applying the molecular dynamics formulation is quite different. So that comes to our modern approach in the molecular dynamics simulation. So as you can see, okay, so let's go one by one. So recent advancement in the computer hardware such as graphics processing unit have made the powerful MD simulation more accessible, cost effective, and allowing them to run locally on the modest systems. So basically, the parallel program of MD that started between 1970s to 80s. Now after that, mostly people use this CPU cores to run the parallel programs, but due to NVIDIA, the sudden advent of the GPU core, now people are using a combination of CPU and GPU to do the computation to do the computation of MD. Now, as I say, the force calculation or the potential energy, the computation of the potential energy is mostly the tedious work, and that requires the maximum amount of time. So there are the specific algorithm parts are given that which part of the potential energy will be computed in the CPU and which part will be computed in the GPU. Has anyone used GPU before here? GPU computation, right? GPU computation with AMD, right? Or MD and DFT. Okay. So basically what happens when we go for a GPU part, GPU is always connected with the CPU. That means this graphics processing unit will always be connected with the CPU. So let's say that's the CPU port and that's the like this way. So that is a GPU. Now our most important thing is the calculation of the forces, right? Calculation of the forces. So force, that is this one. So therefore, right? This is our equation. Okay. So now which part will be computed in the CPU, which part will be computed in the GPU? Based on that, the efficiency of your molecular dynamics program, uh, I mean, the efficiency depends on this one. Let's say I have taken 1000 atom system. I have taken two 1000 atom systems. Some people, let's say if your GPU supplier, they are claiming that you can go for 100 nanosecond or 200 nanosecond per day. But when you are applying, I mean, when you are doing your MD simulation, you barely get 5 or 10. Then you complain with your with the GPU supplier that okay, whatever you claim, that is not exactly happening. But the thing is, you do not see what is your system requirement, right? So let's do the analysis. So let's say I have a 1000 atom system. Mainly this is water. And here I have a 1000 atom system, out of which, let's say 800 atom protein and 200 atom water. So I have two systems. I want to run in CPU and GPU in this combination. So can anybody just crudely answer which one will give me the faster result in GPU? Water. Why? Yes, correct. It is not only small, it has some advantages. Okay, let's say we say that this force calculation is basically will take the maximum amount of time. Now, force calculation will include the bonded plus non-bonded. If I go with the water, so what are the bonded things? Only the OH, and there is only okay one angle. So there is two bonded calculations and one angle calculation for each of the atom. Now, if I submit the job in the CPU, what it will do? It will divide, say 100 atoms. 100 H2O to this particular port. Next 100 water to this port, and in each of the port, it will do the bonded calculation, as well as inside the code, whatever the non-bonded calculations are present within that 100 water molecule, that will be performed in the GPU. Once at each and every step it is done, they will return it back, the information to the CPU, and within that 100 atoms to the first cell and 100 H2 in the second cell, that non-bonded interactions will be computed in the CPU. That means each of my GPU core is well fed each of my GPU core is well fed and the calculation will be faster. But here in in the protein, out of this 1000 atom, that 800 atom is considered 800 atom makes the one protein molecule. So now, as per the simulation, as per my geometry, I cannot give the 100 protein atom here, 100 protein atom here. I cannot give that. I have to allot the entire 800 here, because otherwise the protein will be fragmented. So now all 800 calculations are happening here, bonded and non-bonded, and here remaining, let's say 100 water, 100 water. But remaining my GPU cores will be inactive. So therefore, earlier here for this case, it was computing 100 for each. Now for the second set of simulation, the first one is computing with the 800, and most of them are free. So obviously, this computation will be slow. So therefore, whatever your system is, based on that, you have to choose the architecture. I have seen that many newcomers, what they do when they get a abundant access of CPU and GPU, they try to run any system with respect to this one without analyzing their potential of the system. Okay. So in this kind of systems, if you solely running the CPU, you may get faster result than the GPU. Clear? So based on the system, based how system can be fragmented, you have to understand, and then you use the CPU as well as the GPU resources. So it may be your supplier, your GPU supplier, they have optimized the GPU pace with respect to this atom, but not with respect to your system. That's why they can claim that it is way faster than this one. Right? So whatever your systems are, based on your geometry of the system or how your molecules are oriented, you can choose the computational architecture. Right? Even when we order the systems, when we purchase the systems, we know what computer architecture we require for our system. What is the purpose? Now, whatever those theories, those algorithms, dynamics, barostat, thermostat, those are being coded in either in open source or in the licensed version of packages. Right? So now, and some of the softwares, so user-friendly software packages for the performing AMD simulations are being developed that provide the better support for the non-experts. So some of the most famous of them, these three, Bromax, LAMPS, and NAMD. Okay, so now even without understanding the proper concept of the thermostat code or like the biostat code, etc., or the Langevin dynamics, etc., you can still do the MD, because the scripting part, these codes are available. What you need to do, you need to call the keywords, make the script file, and then you have to run. The only thing still it is not there, that is you have to prepare the input script and the post-processing script. Okay. So, making the input script, just now I was discussing 2-3 of you regarding their problems in their MD part. So I gave some input. So mainly the scripts are almost same. Okay, whatever the script you can use for the ion transportation, the same script you can use for the extraction. Only 1 or 2 changes are present. But making of the input file and analysis of the output, output trajectories are now is the key point. Then again, when we have this CPU come GPU concept, then this parallel implementation is already being done, and that's why the MD gets a huge boost in computation speed. And for that reason, even let's say for your desktop computer, how much we get the speed for the desktop computer? Romans. So even with this kind of, let's say, 8 GB RAM, right? 8 GB RAM, i5, okay, i5 processor we use, we get a 15 nanosecond per day speed. And even for the GPU, we get the 100, like this, 100 nanosecond, which is exceptionally good, we consider, right? And depend, I mean, again, that is okay, that is another thing that we have in my group. I have GPU like A4000. There we get like and we have 128 GB RAM, so we get 18 nanosecond per day. But same in, okay, in the CPU we have only 8 GB RAM, but we get 15 nanosecond. That means our systems, I mean, is not, I mean, GPU, most of the GPU cores are inactive for our systems as well. Okay, we can give more number of atoms to my system or more number of various configurations to my systems, and then we get the optimum GPU, okay, GPU performance. So again, based on your system, based on your availability of the resources, you need to choose. It's not like that you always need a supercomputer, you always need a very, okay, high performance cluster. If you can optimize your system, even if your desktop computers are good or like the workstations are good to run the modern day MD simulations. Okay, so some of the solvent models, I think this has been covered in the DFT part, right? Implicit solvent model. CPCM. The small part is covered, yes. Okay. So again, there are some two. I mean, there are two famous ways that the implicit solvent model. So that is basically very much similar to your quantum chemical calculation. That is polarizable continuum model, PCM calculation. But for the explicit, that is mainly with respect to the water. So when we consider our system is solvated in water, then various models, I mean various models for water, we use that. So in the explicit model, each solvent molecule is represented with a set of atomistic interaction centers, and these are mostly accurate and detailed computation, but these are computationally expensive, requires averaging of the solvent coordinate. Then the water model specifies the interaction site of the water molecule and the partial charges of the LJ parameter. And there is a large variety of the models in terms of rigidity or flexibility, how many points of site we will consider, the polarizability, dissociability, etc. And some of the values like the equilibrium bond length, equilibrium angle, those are defined for various water models. Similarly, in the implicit, the solvent is represented by a continuum described by a macroscopic parameter such as dielectric constant, density, surface tension, etc. for the Cosmo. Instead of the solvent dielectric property, you use the infinite conductor for the Cosmos based models. Okay, so theoretical framework based solvent PMF, potential main force. They are not accurate in terms of this MD computation, but for the DFT they are very accurate. It reduces the dimensionality, relative solvation free energies from single point, effective potential energy calculation, and explicit hydrogen bonds with water molecules are lost. This is one of the drawbacks. Okay, PVC you know, right? Periodic boundary. So I'm not going to this one. Okay. Now the important thing is what we can do with the post processing. So as I said at the start of my lecture, that molecular dynamics only give you the time dependent characteristics. It's your duty to convert them into observable properties. So again, molecular dynamics gives the time-dependent coordinate forces and velocities and convert them into value into valuable property. So first one is it is not a time-dependent property, but rather a distance-dependent property, the radial distribution function. And again, I say that up to 2008 or something, if you can compute the radial distribution function of a complex system, you will get a JPCB paper. Nowadays, you will get nothing. Okay, so what is this RDF? MCVB तो पढ़ा गया था. What is RDF? Okay, radial distribution function. It's not taught, right? Okay, so RDF basically that is giving the three-dimensional orientation of a system. Let's say again I take this example. So this is the ionic liquid. Okay. LiTFSI. Now I want to know that by centering the lithium, how many TFSIs are present? What is the distribution of this TFSI with respect to this lithium, or vice versa? Or what is the distribution of this fluorine atom with respect to the Li? So essentially, if we plot all of them, eventually we get the idea how the molecules or the constituents are oriented with one another. Which one is making more interaction, right? So let's say I take the Li first, and I want to make the distribution of this one. So now if I want to make the distribution of the whole, I cannot take the whole. The best way is to take the center of mass. Let's say the center of mass is this one, N. And okay. Now, with respect to a particular distance, how many N are present in the three-dimensional space, that is represented by RDF in a two-dimensional space, right? Which means that RDF basically defines the probability of finding another atom by centering a particular atom. So here you can see that. So that says that the density of a particle varies as a function of the distance from a reference particle within the system. That means my reference particle is Li, and based on that, I want to know how many this TFSI with a center of mass as air is present around it. So here, if we do this, if we do this computation, we can see that up to 1.5, I mean, before this minima, there is a huge number of peak between 1 to 1.5. That means if I take this Li and N, let's say example, altogether, then they are very close. And if we do this area under the curve of in between 1 to 1.5, we will get the number of N present, number of N surrounding the Li. And that number is called coordination number. It is not present here. Okay. we'll see that that number is called the coordination number. So coordination number is nothing but the area under the curve. Clear? Area under the curve. So here this one is the first minimum, right? At 1.5, that is the first minimum. So at 1.5, it is called the first solvation cell. This 1.5 is called the first solvation cell. So you can see that during this first solvation cell, very high number of N negative, that means this one is present. That means Li and N, they are very closely interacting. They are very closely interacting. Okay, but after the first solvation cell, you can see for the second solvation cell here the number of N negative is not that much. So around this one, with this respect to the first solvation cell 1.5, if we draw one sphere, we will see that maximum number of N negative, that means the TFSI anion are present within this solvation cell. For the second solvation cell from 1.5 to let's say 2.5, that is the second solvation cell. We will find not that much number, but very low number. Again, it is like the area under the curve. Okay. Similarly, at a very long distance, it can go to 1. That means we will not find any kind of TFSI in this one. So now I can plot with Li with respect to F, because that's a cation electropositive. This F is a electronegative. I can also plot Li with respect to oxygen. Okay, and based on that, based on the peak, based on the sharpness of the peak and the value of the CN, that means the coordination number, I can get how the Li is oriented around TFSI anion, whether it is very close to N or very close to oxygen or very close to fluorine, etc. Right? That's now, although in various books the RDF codes are present, but still with the given trajectory, you can compute the RDF from the VMD itself. We'll see after in the second half. I mean after tea break, how to do it. This clear, right? So RDF. Why it is converted? Because it's a probability factor. It is not necessary that it will convert to 1. It is not necessary, and also there is a gap here. Why? Because Li can come only with a certain distance of N. If it cannot come beyond this allowable distance, because if it comes beyond this allowable distance, then there will be a repulsion effect. Remember that the LJ potential curve, slanted. Okay, in some cases, specifically for the polymeric system, we get the RDF like this way. It will not convert to 1. So what does that mean? That means that there is a very high degree of steric hindrance present at the core or whatever the functional group you are considering to plot the RDF. Whenever that steric hindrance is removed, basically in the longer distance, I mean at the periphery of the polymeric chain, there you will find more amount of interaction. But in this part, at the very core of the polymer. The steric hindrances are present. That's why the two atoms or the two functional groups cannot come very close to each other. It is not that always you will get a convergence at 1. It can be in the divergence region. Okay.
Now the maximum correlation for if the reference atom is maximum down to 1 angstrom, find the maximum probability the other atoms are surrounding that symbol. And then why it comes down? Because once there are a ring of atoms around the central atoms, it will not allow other atoms to come near to that. So the chances of getting other atoms is less, so that it is dipping the. Okay, because of the steric hindrance, it is not allowing another layer of atoms to come to its neighborhood. Then again, if you go further distance away, again you get correlation, but the lesser distance compared to the function. As you go higher and higher distance, the correlation is totally lost. So entire represents 1 within 1. So all the atoms are randomly. So whatever you measure the density of the atoms will be the same at long distance.
Thank you, sir. Okay. Next one is the hydrogen bonding. So here you can see that even the hydrogen bonding, it can be measured with respect to the RDF, but again the specialized packages are available in the BMD to compute the hydrogen bonding. So generally we take that if any non-bonded interactions come involving the hydrogen within 0.35 nanometer, it comes under the hydrogen bonding interaction. And then there is also one more thing, that is the angle should be less than 30. That is the general consideration considered for the hydrogen bonding. Okay, so these are basically the structural part. Now, next, the important thing is for the MD, we need to compute the transport part. So in the transport part, we have a concept called auto correlation function, and depending upon what you want to measure this auto correlation function, it becomes the velocity autocorrelation function or VSEF, which can be used to measure the diffusivity. Then we have electric current autocorrelation function or ECACF, which can be used to measure the ionic conductivity. And then we have the pressure tensor autocorrelation function or PTSEF, which can be used to measure the viscosity, right? So basically this autocorrelation function, it measures the correlation between the property at time t and time t prime. Here, obviously time t and 0, obviously, okay, and time t and t prime. And this curved brackets, these are the ensemble average, right? So ensemble average we already have discussed. What is ensemble? Okay, so at first, I mean, other than the autocorrelation function, we can also compute the diffusivity by measuring the mean square displacement. Okay. So it measures the deviation of the position of a particle with respect to a reference position over time. It is the most common measure of spatial extent of random motion used to characterize the diffusion of particles of various systems. Now, I must say that this diffusion is the self-diffusion. This diffusion is the self-diffusion, when you do the molecular dynamics, then you get the self diffusion. From the self diffusion, you can convert it to the binary diffusion, but that binary diffusion is called the Maxwell-Stefan binary diffusion. It is not the fixed binary diffusion, right? And there is a particular correlation to convert the Maxwell-Stefan diffusion, binary diffusion, to the fixed binary diffusion. Okay, so here whatever the diffusion we will get, that is the MSD, that means mean square displacement. That is okay, displacement with respect to its immediate predecessor squared and then ensemble average, mean square. So if we write it with respect to the discrete formulation, then we get this MSD, we get this formulation, and the differentiation of the MSD with limit will give me the self diffusivity. It's not the binary diffusivity, but the self diffusivity can be converted to the binary diffusivity, but that is the Maxwell-Stefan binary diffusivity. Okay. We do not get the fixed diffusivity directly from the MD simulation. We get the Maxwell-Stefan diffusivity. That is not related with respect to the reference frame. Okay. Viscosity. Obviously, what you know the viscosity. I will just explain this term. Okay, so now to calculate the diffusivity, we have two ways. Like to calculate the viscosity, we have two ways, just like the diffusivity. For the diffusivity, we can calculate either by velocity autocorrelation function or by Einstein relation, this one. Okay. Similarly, for the viscosity, either we can compute with respect to the Green-Kubo relation, or there is a relation called MSSD, mean square stress displacement. MSSD, mean square stress displacement. That is very similar to the Einstein relation, but I am not going to discuss that one because that's not a very reliable method. Okay, but what I will discuss is the Green-Kubo method. So the Green-Kubo relation for method is used to calculate the viscosity of a fluid in the MD simulation based on the time correlation of the off-diagonal component of the stress tensor. The importance of the Green-Kubo relation in the viscosity calculation lies in the ability to provide a direct link between the microscopic behavior of the particles and the macroscopic property of the viscosity. Okay. So just a particular notation is that although during our development of the Verlet algorithm, leapfrog algorithm, we have seen that from the position vector, we can compute the force, we can compute the velocity, right? Now, the thing is, for our case, I mean, in our simulation, if we want to try to apply that, we will accumulate large amount of error. That is practically observable. Even once, okay, I tried that, I had accumulated very huge number of error. So whenever you are computing the viscosity part, you calculate the force, calculate the velocity, calculate the trajectories, time dependent from the program itself. That will reduce the error because in the program they use the sophisticated algorithms to minimize the order of 4 or order of 3 errors. Okay, merely using the Verlet algorithm or leapfrog algorithm, excluding those order of 4 or order of 3 error will accumulate very large number of errors. Okay. So whenever you are trying to compute the viscosity, try to get the force as well as try to get the velocity from the code itself. That means from the MAMD, GROMACS or LAMPS code itself. Save those files. Those files will be useful here. Now, how this is? So this is my viscosity. Again, the molecular dynamics only gives us the time dependent trajectory as well as time dependent force, because forces can also be computed with respect to the trajectory. Velocity can also be computed with respect to the trajectory, right? So this is the this is the PTSEF. Now, what is this one? So PTSEF, that is average, I mean that is integrated over the entire time duration. And what is this one? That is the volume of simulation box. That is the Boltzmann constant, and this is the temperature at which you want to measure the viscosity. Now, as I said, that molecular dynamics will only give me this kind, only give me the trajectories. It is your duty to convert those trajectories into particular observable part, like observable property. This has only come to balance the unit of viscosity from here. Otherwise, in some of the articles, you can see that some of them have used a different formulation because the stress tensor calculation is different. Some of the researchers, they have used a different sort of denominator or different sort of scale factor just to get a minimized error. So this has only come to balance the unit of the viscosity from the stress tensor, right? Okay, so that is the P. P is the stress tensor, which is with respect to time t, which is dot product with the stress tensor, just its predecessor. That means the previous time. Okay. Now, alpha and beta are basically the directions. So alpha, beta can have 3 values, x, y, and z. Alpha and beta can have 3 values, x, y, and z. If alpha, that means xx, yy, and zz, then these stresses will be the normal stress, right? If alpha equal to alpha, that means xx, yy, and zz, that means these stresses are normal stress, right? And that time alpha equal to beta, so this is my Kronecker delta. So the Kronecker delta for alpha equal to beta value will be 1. So if we want to get the pressure tensor, if we want to get the normal component, the normal stress, that time only this Kronecker delta will be activated, and we will get the normal component. For other cases, for the shear stress, as alpha is not equal to beta, so then the Kronecker delta will be 0. The Kronecker delta will be 0, and then we will get the shear stress. Clear? So with this same expression, either we can get the normal stress or we can get the shear stress, right? So alpha and beta, it can be x, y, z, the 3 directions. Now, what is this one? So this is this is the stress tensor. This is the simulation box volume. That is the mass of a particular atom. Now that is I direction. Okay, I direction, that the velocity of ith component at x direction. Let's say this is x. velocity of ith component at x direction, that will be multiplied in a dot product, will give me the velocity of y direction. Let's say this alpha is x, that is y. I mean beta is y. So I am getting the stress tensor, shear stress is sigma xyt. So that is alpha will be x direction velocity of ith component, beta will be the y direction velocity of the ith component. Similarly, this r is alpha direction. That means x direction I j. That means with its nearest neighbor, because j is not equal to I. So that is the distance of nearest neighbor times the force of the other direction. That is, I mean, okay, let me explain. So let's say sigma, that is, let's say alpha equal to x and beta equal to y. So that will be xy. Okay, let's say that will be for x, y. That means, okay, what we require? Okay, to get that x, y direction shear stress, we have to run the summation through all over the atoms. All over the atoms, each of the atom mass will be multiplied of x direction velocity with respect to the y direction velocity, and that will be summed up. Clear? That will be summed up. In the next case, we have the force component. We have the force component, and we have the distance component of I and J. Let's take let's take the water. So O H H X Y Z. Say time equal to 1. O H H. X Y Z. X Y Z. Now time equal to 3. Again X Y Z. Y Z. X Y Z. Okay. So this part is clear. This part is clear because this is my distance. The same way I will get a velocity, I will get a force file. 3 files. So for the velocity, let's say I want to calculate with respect to the time equal to 1. Okay, time equal to 1. So mi, that means mass of O, with respect to Vxi, this one, Vxi, and Vyi, that means Vy here. X with this one, X with this one, X with this one, all these cases. This is basically the okay vector. So Rxij. Now Rxij, that means Rx of this one, that is the ith component, and Rx of this one, that is my jth component, right? This is basically my vector addition, and this is also my vector addition. So Rxyj, how it will be? This is my vector addition, right? Rx I, Rxj. Now, if I remove the vector, then I will get the resultant. Okay, resultant distance square root of Rx square plus R. Okay, Ry square. Then similarly, I have the F component. That is again the vector. Remove the vector, I will get the resultant component. So those components I have to compute in separate column, and then okay, then I have to multiply it. Yes, individual atoms Rxij. Rxij is the resultant distance vector at x direction. No, that's only the x component, because here what I am taking, alpha is x, beta is y. Similarly, if alpha is y, beta is z, that will be different. Ij, this is I equal to 1. This is I equal to 2. This is I equal to 3. Now here j will be not equal to I. That means 1 1 is not acceptable, because if it is 1 1, then it will go for the pressure tensor. But I am doing the stress tensor. I am not doing the normal stress. I am doing the shear stress. So shear stress I will be not equal to j. So I is not equal to j. So if this is I, then these two are j. Right? Clear, no? So this Rxij bar, that is the x directed distance vector, resultant vector between I and j. That means x and x, x and x. This one. Similarly, f is y directed resultant vector between this and this, this and this. Then you have to run two loop and add it. So that is the shear stress between x and y. Yes. Okay. These are basically no. No, that's another dot product. That is a cross product. Okay, cross product, because you can see that alpha and beta is not equal to beta to alpha. Okay. Whenever this alpha and beta will be changed with respect to beta and alpha, this entire product term will change. Clear? So although it is looking like a two summations, but when you do the computation with respect to, let's say, 50,000 or 1 lakh number of rows,
That part. The resource. In term, we are trying to get the resource.
yes,
That is an integral of the closed time integral for the two states, but two different time states. Pressure at two different times. In that case, alpha and beta denoting that any two molecules that we are trying to.
No. Alpha and beta are the directions, x, y, z directions, because we are doing the stress tensor, shear stress. When alpha is equal to beta, that means xx that will not be the shear stress, that will be the normal stress. That time the Kronecker delta will act. Otherwise, for the shear stress, the Kronecker delta will be 0. We will only get this one. But sigma of alpha beta is not sigma of beta alpha because this is not a dot product. This is a cross product. Clear? It is difficult. Even when I did the programming, it took me 6 months. Because this is you are doing for one direction at one instant. If you are running a 10 nanosecond with a 10 nanosecond simulation with 1 picosecond, then okay, how much? You will have probably 1 nanosecond. 1000 into 10,000 rows. Right? 10,000 rows to compute this sigma alpha t. And from this sigma alpha t, we will get this p alpha beta. And from that, the immediate, I mean the current one with its immediate future, okay, will be multiplied to get the ensemble average. So many factors are present. That's why the green Kubo, when we do the green Kubo, we do not take the entire length of simulation. We just take a very small part of simulation where the fluctuations are not too much. Clear? And maybe little bit difficult to understand until unless you start the programming, you will not understand. I mean, there are basically 3-4 concepts two concepts, okay, are merging. One is the direction, X, Y, Z, that is the stress tensor. Another one is the particle. So particle that is mixing with the direction. Clear? But anyway, you can follow my papers. I have done in some of the paper, 2 papers, this kind of computation. Although the codes you have to write. Is this code available in someone? This specific code? So that's why this green Kubo is still challenging, because when we plot the green Kubo, then wherever we get this plateau, only that part, let's say if it is a 200 picosecond or 500 picosecond, we only take that one. We do not take the entire length because the fluctuations are too high. And due to the presence of these 2 terms, the diffusivity, the viscosity has wide variation. Okay, so that's one kind of post-processing thing. One kind of post-processing thing that you need to figure out. Okay. So next is again the ionic conductivity. The ionic conductivity is again calculated by the green Kubo method. Basically, there are 2 methods to compute the ionic conductivity. One is the green Kubo method. Another one is the Nernst-Einstein method. So basically, the Nernst-Einstein, what is the difference between Nernst-Einstein and green Kubo? Nernst-Einstein that did not consider, that does not consider the inter-ionic part. That means the interaction between cation and anion that they ignore. And this dcat and dan, basically the self-diffusivity, basically the self-diffusivity of the particular ion. Okay, and these are the particular charge of cation, particular charge, numerical value of the charge. Let's say if it is a LiTFSI, so it is a 1 square, and that is -1 square. Okay, but when we go for the green Kubo method, that time we consider the ECACF or this function, and this is the complete integral which is converted into this discretized form here, and this one, so that is the ECACF function. You can see there are two things. So first one is the cation. That is again the product. Then anion. And after that, as these two are the vector signs, so cation anion and anion cation will be different. That those velocity files, I mean, you have to compute this from the velocity file. Although, as I said that in the integrator scheme, you get this velocity, you can get the velocity from the velocity varlet or leapfrog, but you will miss the sophistication of these computational programs like NAMD, GROMACS, and LAMS. So therefore, it's better to extract the force file, extract the velocity file, as well as extract the trajectory files to get this data. Okay. Okay, that's the end of session. That is the theory part. Anything you want to ask? Question?
We have diagram solution and we are trying to find the ideal solution. Then which method will be video?
Okay, what is your system?
I am doing lithium in Robert, taking division and
Only lithium.
lithium with the salt, motion salt of lithium. It is a direct solution.
Do you have the, I mean, anionic part in the solvent? Then I think that the green Kubo is better.
So since it is a dilute solution, so we are considering that it is completely okay. Dissociation occurs, then the ions are moving freely.
In that case, you can do it for the NE. Okay, Nernst Einstein method. So, okay, here is a catch. You can take that at first, you can take that lithium as the +1 charge, so 1 square, and then that will be the -1. But if your simulation, let's say the diffusivity, etc., are widely deviating, then you have to scale your charge, and that scale charge, let's say 0.8 times, 80% scaling. That 0.8 will be multiplied here. Right? That time. But I mean, this is theoretically very accurate, but again, implementation is very difficult. Computation. Dilute solution, you can try with this one. Try with this one. But for the ionic liquid, what we do, we generally use this one. Ionic liquid or depurated solvent, the neutralic solvents, we use this one. Shall I take a very small part of the GROMACS and then we'll continue? I mean, okay, we'll go for teas. I think 15 minutes will take. 3:30. I'll continue. ये रोगीपुर कहाँ पे है? GROMACS tutorial. Okay. Let's start. Just briefly, we will take what is the GROMACS and how to do the simulation that we will go through after the tea break. Okay. Okay. So this is molecular dynamics simulation with the GROMACS. Okay. So in the previous session, we have understood some of the part of theoretical aspect of this MD and what we can do with the MD. That we have seen. The question is how to do it. That lies on the simulation technique. Okay, nowadays most of the things are being coded in the open source or licensed version of the software packages. So we need to learn the simulation techniques to apply our theory to do the application. So it says that in this simulation technique, we have three things. First is the preparation of input files. So preparation of input files, it contains the coordinate files and the topology. Then we have the configuration script. So I will give you how to do the configuration of energy minimization, equilibration, as well as the NPT, NVT simulations for the GROMACS. And then analysis of the output file means analysis of the trajectory, whether you want to do the RDF, MSD, diffusivity, viscosity, etc. Okay. So for the configuration script, we use different source of different types of MD packages. Some are the open source package, some are the licensed package. So open source package, GROMACS, NAMD, and LAMPS, those are very widely used. Amber, Charm, as well as the Material Studio are the licensed licensed packages. Out of them, I think Amber and Charm are relatively cheaper, but Material Studio is very expensive. Okay. So why people use open source package? Because these are developed and distributed free of charge. That's the first and foremost criteria. Flexibility with input, output files, and the configuration parameters. Flexibility with programming languages. And the most important thing is the build the network. So in a molecular dynamics, there is a say that don't think that you are the only one who get this error. There is always someone else. So whatever the error you will find, just copy the final lines of the error or the log file and paste it in in Google. You will get some have already encountered this problem, right? So now, based on their solution or based on the mail, subsequent email, you can build your network. And people used to do it for any kind of simulation process, whether people follow the ResearchGate or LinkedIn, or people follow like the mailing list. Based on that, the network can be built. That is another objective of using the open source packages. Coming to the GROMACS. GROMACS, the full form is the Groningen Machine for Chemical Simulations. It is developed by the Hermann Benson Group of this Groningen University. That is open source package. Download from this, you can download it. This has the architecture specific source code that is also available. The present stable version releases this one, and it has a wide community as well as the tutorial people support. So what this tutorial will give, that is the installation of GROMACS, preparing the input file, writing the GROMACS script, analysis and the trajectory data of VMD and GROMACS. Installation, So in the Google, if you write the GrowMax, you will get the first of this website link. Then when you click there, you get welcome to GrowMax and several other useful information. Then you get your desired version from the download section. You can download the tar files or the compressed files. And after that, these are some commands specifically for the Ubuntu or like CentOS type of Linux terminals. So there they will get, you do this, okay, you write one by one the subsequent libraries that will support the GrowMax. And the quick installation of the GrowMax after downloading that, you have to untar it, then you have to go to the GrowMax folder. Okay, you have to create a build directory, go to the build folder, then you have to use this make command, and then inside that you go to the make install command, and then it is installed. When you install, you will get a very good port. That's the same kind of quotation, ports you get it at the end of your successful run in Gaussian. Okay. So can we take break? I think this will cover a lot. So we'll start this after 3 days. Okay. We get a feedback. So, without a password, carrying out it now, that also we expect the initial